Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Koronis Rift, published in 1986 by Activision, developed by Lucasfilm Games. The coder was Arik Wilmunder and Noah Falstein, and the musician was Douglas Crockford. Box artwork was by Terry Hoff. I had the tape version of this way back in the day, but we're going to be looking at the disc version. Like Rescue on Fractalus, this uses a very similar kind of rendering engine, almost exactly the same, I would say, by looking at it. And it really sparked my imagination when I had the tape version way back in the day, when I was very much younger than I am now. I would imagine myself wandering around the mountains and the valleys and trying to discover lots of hidden things. Of course, there weren't hidden things that really of that detail anyway in the game, but you know, my young imagination would go off in flights of fancy. The graphics on this were, I would say, groundbreaking for the time. They don't look very good these days, of course, but for a 1 megahertz 6510 processor, they look really good. This is, of course, a bitmap screen. Actually, it looks like it's two bitmap screens because the TV screens on the top and the screens on the bottom and the status panel on the bottom are different to the stuff which is in the middle of the screen. And the middle of the screen is this kind of like iconic robot in front of a conveyor belt with computer banks around the robot. When I had this game, I did not have the instructions. So I didn't really know what I was doing, but I just kind of enjoyed running around on the planet's surface. And we can see here quite clearly that there are two double buffered bitmap displays. The bitmap on the left, in bank 8000 in hex, contains the upper and lower status display. But the bitmap on the right, which is in the bank starting at C000, does not contain status panel on the top and the bottom. It just contains the landscape in the middle. Using Vice, monitor debugger, and also using ICU64, we can quite clearly see that we have some sprites there. Of course, the sprites need to be in both banks at 8000 and also at C000, because the sprites are, there we go, dynamically updated as the UFO and as the red spaceship thing comes onto the screen. We can see that they are dynamically updated sprite frames. And as the, there we go, and as the UFO goes flying around, the sprite frames dynamically update. So the dynamic update for the sprite data there is, of course, because the graphics are sometimes obscured by the landscape. So the sprites need to be dynamically updated to reflect that. There's no sprite background priority being used here, and that's because we've just got this bitmap screen in the middle. And we seem to have the kind of light grey colour seems to be the background screen colour, and then we are using two colours for the landscape in the foreground. I've just run out of energy. This is an original disk image, of course, so there's no cheats. So I was, looking at the landscape and not really concentrating on how much energy I had. So I think I died. Let's warp past this, and there we go. In warp mode, it loads a lot quicker, doesn't it? But we can see here quite clearly now that the red spaceship is behind the landscape. Look, the dynamic sprite only contains the visible pixels that you want to see for the spaceship. We can see that it's, even though the viewpoint is stationary, we can see it's rapidly rendering into two large areas in memory, and that corresponds to the graphics map data for the bitmap screens, both of them. So let's see if we can delve into the game bitmap drawer, if we notice, look in the memory map, there's no update of the color map data, apart from the color map updates which have already been applied to the color RAM for the status panel. So the middle of the screen doesn't have any color RAM updates. So we're just looking at updates to the bitmap data. So we know where the bitmap data sits in memory because we can see that. Well, we know roughly, right? We know it's at 8000 plus 2000 in hex. So we know that that's going to start at A000, and the other one starts at C000 plus 2000, which is E000 in RAM. Let's see if we can find out the exact memory range for the middle portion of the bitmap display, because then when we find the exact portion for the memory range for the middle portion of the screen for the landscape render, then we can put a watch store point on that memory range. We don't really want to get any updates to the score panel mixed in with this watch store point, so that's why I'm looking for the precise memory range. Well, that was a good guess, but it's not quite correct. Look, let's subtract a little bit to include those last characters, A780, and we'll fill it with FF this time. Well, there we go. That's a good guess for the start of the landscape rendered data. Now let's see if we can find the end memory address for the end of the landscape data. There we go. It's nearly there. We've got one character row plus a few characters. So let's go up in, okay, there we go. Let's just add on 7F there. I think, yep, there we go. So the A780 to B67F is the entire memory range for the bitmap graphics data for at least that bank of the bitmap screens and for the landscape render. So we're going to do a ranged watch store point between those two memory addresses. Now we're currently actually rendering, well, okay, so that looks like an unrolled loop of stores. Well, it's an unrolled piece of code, it's not an unrolled loop. It's unrolled speed code, there we go. For all of those stores, yes, it's rendering into that bitmap. So we've halfway through interrupted the rendering for the bitmap screen that we're looking at currently. So let's delete all of the breakpoints. Let's see if we can catch this routine from the beginning of when we're actually storing or rendering into that graphics bitmap, rather than halfway through, shall we? So let's just see what these other routines. Oh, that drew some lines. Okay, so I think that was the routine just before 8B3 there, right? I think it was. But we'll get around to that later on. So I'm pretty sure now that this second iteration through the code is going to be rendering into the other bitmap screen, right? So the current screen, which is now visible in the C64 emulator, is the one which was filled with 0, which is that screen there in the debug graphics map. So I think we're currently rendering to, or we were rendering to the bitmap screen. Now we should be rendering back into the currently visible bitmap screen in the graphics map debug view there in ICU64, the window on the right hand side. So let's see if we can figure out what some of these routines do. So 8AD JSR to CH69. Well, that rendered in solid colors. It rendered the landscape, right? And now we need to figure out what these other routines do. But there's more detail to that landscape render than just hopping over the entire JSR to that entire routine. Well, that drew lines as well, right? We're now into the next frame, I think. So let's get back to the frame that we want to actually get to. There we go, fill the screen again. So now we're back into the next double buffer iteration through the game. So now we can step into that routine there that was at 8AD with that JSR, and now we're at C869. Good. So now we can step through this code to see exactly what does the drawing. Now, I think we've already seen that we've had that large block of code which did a whole bunch of store accumulators, absolute address, and then comma x on the end, right? But how do we get to that point? That's probably one of the more important things in this game, because the game actually renders very quickly, considering it's a 1 megahertz 8-bit processor, and the screen is enabled, of course, which steals some CPU cycles because the VIC chip is active. And there are sprites on the screen, which also steals more cycles from the CPU. So considering all of the, considering how few cycles there really are, this CPU is doing a very good job of rendering such a view. So, okay, we've got some code. Yeah, that's the other bitmap screen that's done all of the rendering so far. We seem to have a load of accumulators CEAD as well, which I think probably looks like it's doing some kind of like table lookup perhaps, or something like that before rendering into the bitmap data. We'll just put the other bitmap view with the bitmap which starts at E000. We'll just put that one there in the bottom right hand corner just so that we can see what the previous frame looks like. So now we're currently rendering into the frame, right? So let's have a look. What is this indirected memory address here at 797A? Oh, okay, so that's storing something into CD00. Oh, there we go, look. So the code at CD00 is the code which we can see at the start of the bank there. But yeah, look, it's storing 60, which is actually an RTS. 60 in hex is an RTS instruction, which is done from subroutine. So this code seems to be self-modifying that unrolled speed code for doing this store, and then it seems to be JSRing into the middle of this block of code here. So if we do some steps, there we go, we can see that the accumulator, it contains FF, which is a solid color, and we can see as we step along, we saw that column of, or the column of 8 pixels across, gradually moving up the debug bitmap there in the graphics map view. So as we step through this code, as we step down through the code, the column of pixels is drawn upwards from the bottom, which is, it kind of makes sense, right? Because if you do some calculation on 3D points and then project them and stuff, it kind of makes sense to draw from front to back. If you have no overdraw or anything like that, there we go, it's RTSing now. Okay, so if there's no overdraw, then you can quite comfortably draw from front to back. And then you can just draw straight up the screen, because you know that at the bottom of the screen is going to be nearest to the camera, and then as you progress up the screen, it's going to be furthest away from the camera because of perspective. So this routine here, which JSRs into that unrolled block of instructions which do store accumulator, absolute comma x, it's self-modifying them, look. So it's restored back the opcode 9D, which is store absolute comma x, absolute memory address comma x, and it's then putting an RTS into the code, and then it's calling into this routine again to then draw in an optimal way a column span. So it's not just drawing a simple column, it's actually drawing, by the looks of it, it's drawing multiple spans of pixels vertically up the screen, vertically up the bitmap screen. So yeah, I think this is using really quite clever self-modifying code. Self-modifying code is where you store data into code that you're going to execute, and this data can change the opcodes, it can change memory addresses, it can do other things as well. It could change, for example, branch destinations or jump destinations or JSR destinations. So this self-modifying code is usually one of the quicker options that you can have for executing code quicker, because you don't have to have compare and return and branching and stuff like that. You can just optimize the code by self-modifying it to actually get the behavior that you want. So yeah, this column draw seems to be basically drawing spans going up the screen. So we've got this JSR at C902, right? And it self-modified the JSR. So the destination address is modified, and that basically jumps into, yeah, you see it's drawing a span of 5 pixels vertically now. So yeah, it really is quite a good way of optimizing your span draw. If you know that horizontally you're going to be drawing all of the same pixels for the 8 pixels, or rather, because it's in multicolor bitmap mode, for 4 pixels horizontally, because each high resolution pixel is 8 horizontal high resolution pixels equates to 4 horizontal multicolor pixels, okay? Because you've still got 8 bits, and each color in multicolor takes 2 bits. Anyway, so yeah, this is really clever because it's, in an optimal way, it's drawing vertical spans of columns going up the screen. And it's indexing that with comma X, and that's because if you index it with comma X, then you can move, if you add or subtract 8 from these values, then you can draw columns to the left and columns to the right, because each column is separated by 8 bytes, because you've got 8 bytes for the vertical character data, if you like. Each 8 by 8 pixel block in the bitmap data is organized as 8 bytes. So yeah, this is a really good, really optimal way of drawing vertical spans of a solid color, because you just need to set the accumulator once, and then you can jump, or JSR, into this self-modified unroll code to choose the precise span of pixels that you want to draw. So if we fill the bitmap data with a repeating pattern that we know what it looks like, there we go, we can see how each span of vertical pixels is drawn as I debug through this. And the last JSR there at C92B has a load accumulated with 0, so that's doing the fill with the background or transparent color. Color 0 is transparent in bitmap, multicolor bitmap mode anyway, so the background color will shine through. So yeah, this is a really good, really well-coded, self-modified, unrolled vertical span draw. And it makes sense to have vertical columns, because if you're going to be doing kind of like a vertical raycaster, if you're going to be casting rays to the left and rays to the right from the middle portion of the screen, and then drawing that way out from the middle outwards, or from the middle to the left and then the middle to the right, it makes sense that you want to draw these things vertically rather than trying to scan horizontally and to optimize the draw like that. So that's really quite cool. So that's the first routine kind of understood. We do have these lines drawn after the main columns are filled in. The extra detail for the landscape, right? So it's not just mid-grey and dark grey for the mountains. We've got these extra definition kind of lines which move towards us and move around as the player moves around the landscape. So let's see if we can figure out exactly where those extra definition lines or those contour lines are being drawn, right? Now, because it's doing an optimal draw for the spans, it's not doing a fill. Like in some other games where it would draw the top edges and then it would try and do an optimized fill from bottom to top and then mirror the data, right? It's not doing that. It's actually calculating the optimal spans to draw. So it's drawn the optimal spans there at that routine there at 8AD, right? But 8B0 has another JSR. So let's see if we can copy and paste this code. We'll copy and paste the code and we'll just put that into the debugging notes text file. Of course, I will be committing these debugging notes text files, as I usually do, into my GitHub repository, and I will add a link to this specific text file in the GitHub repository in the video description below. I'm just adding some debugging notes here. So this routine at C869 draws solid columns using self-modified unrolled code. So, you know, if you have a loop, right, then you would have, store, x, absolute, x, and then you might have a decrement y, and then you do a branch and not equal to back to the store. And, that's a very small, tight loop, but it's not very quick because you're wasting cycles doing the decrement y, and you're wasting more cycles doing a branch and not equal, and you might have a compare in there. Whereas if you have the unrolled loop, the unrolled code, you're just basically unrolling that whole loop, so you don't have to do any counter update and you don't have to do branch. So yeah, it's a lot quicker. So unrolled code is a lot quicker, and basically, but it does use up a lot more memory, right? Because if you unroll all of that code, then you need some memory to store all of that code, right? So we found where the landscape lines are drawn. Let's just have a look at the dynamic sprites in a little bit more detail. So if we want to find out where these sprites are being updated from, then we need to, like we did for the bitmap draw, the easiest way is to try and fill the data for the sprites with something that is obvious for the debug graphics map view there. So we'll just look for the sprite data by doing an ms command, which is memsprite, right? And we'll just see if we can find where those sprites are in the particular RAM range. We'll just keep on going. It's going to be, these are the sprites which are across the top row of the debug graphics map. There we go. It's sprite 8400, of course. I keep on forgetting this, don't I? If you watch my other videos, then each row corresponds to 400 hex bytes in size. So there we go. Let's fill 8400 to 8500 with FF, and that's going to be the first 4 sprites plus an extra row of 8 pixels. Let's make that H6FF. There we go. I think that's all of the sprites definitions that are used when it's rendering, right? So now, if we go back, well, there we go. We can see in the rendered view there that because we've filled all of the sprites that are currently drawn on the screen, then we have nice, great big boxes of sprite data. And of course, I think I've just killed the targeting cursor as well, or the crosshairs. I've filled over those. So we know the memory range. So this is the kind of like the draw loop, right? Or the JSRs which form part of the draw loop. As I step over these JSRs, nothing seems to be rendering into those sprites. Oh, it was the off screen. It was the screen not currently drawn. There we go. I think this is the currently drawn. There we go. It was the code there. So it was that JSR there which updated the sprites. So that's the sprite draw routine, right? Sitting there. Let's just double check. If we step over dink and then step over again, JSR to 8E1, JSR to 8EF. Hasn't updated that sprite yet. And there we go. So it's 8B9, JSR to 8EF, which draws the sprite data draws the dynamic sprite data with occlusion, right? Because the sprites are occluded, or sometimes the sprites are occluded. We can quite clearly see the occluded sprite there, or partially occluded sprite there. We can see kind of like the little triangle cut out of the sprite data there. There we go. There's the transparent triangle, and that corresponds to the ridge line of that particular part of the landscape. So that really does prove beyond a shadow of a doubt that there's quite a lot of calculation going on in this game for calculating dynamic occluded sprites. Is there anything else in the... Okay, so the algorithm is purportedly it's meant to be based on a fractal landscape, hence the name Residue on Fractalus, and also Koronis Rift that we're looking at here pretty much uses the same algorithm. Visually, it's very similar, right? They hail from a common ancestor, I think you could put it like that, which is fair enough. You know, if you spend a lot of time and effort in investing in a particular engine, then you probably want to reuse it at least, you know, more than once to try and get your money's worth for the investment cost of sinking so much time and effort into actually creating such a nice rendering engine, right? So we can see here that it's doing a load with the screen data, bitmap screen data, anding it with something 5E36, for example, and then storing it back into the same memory address. And that memory address corresponds to the bitmap data. So let's concentrate on this bitmap here. I'm just interested to see what this line draw is doing. So the decrement with 7D branch are not equal there seems to be, yeah, going back. So it's reading in positional data from what looks like a table, comma Y, doing some calculations, and then storing it into 8A, 8B, which is the indirected zero-page memory location for this bitmap data. We seem to be getting, yeah, look, it's storing pixels there into the debug graphics map bitmap view there. So let's put some breakpoints. So we'll put a breakpoint just after the store, stepping through. Yeah, look, you see. That's, yes, of course. So it looks like lines, but it's not completely lined, right? No, it's not at all. Each dot seems to correspond to the highest point. Now, for the ridge line coming directly towards us almost, then the line is not, the line is broken, it's dots, right? But the lines which go horizontally are almost unbroken, but they're not completely unbroken. So it's not really lines, is it? It's dots, and it's just that the dots, depending on if they are coming directly towards or mostly towards the camera, or going at 90 degrees or almost 90 degrees to the camera, then you're going to be getting dots or lines. There we go. If I rotate it around, you can quite clearly see that it's dots of the kind of like the highest ridge line, if you like, of certain points. So each column has maybe 2 or 3 highest points on the screen that it's drawing lines with. That's interesting as well, because I filled the sprites with a solid color. then the sprites which I used, which appear over the status panel, there we go, look, yeah, okay. So usually that block of solid color that you can see, which is attached to the flying saucer as it's flying around, usually those would be transparent sprites. So the easiest way of getting the sprites to clip within that narrow horizontal window and to not obscure the status panel is to not try and remove the sprites, because it's harder to time that precisely, and you could only really move them left or right. You could try and move them vertically, but it's very, very difficult to do that. What it's easier to do actually is to just change the sprite definition in that visible portion of the screen to point to an empty sprite, and then it looks like you're clipping the sprites to within that narrow portion of the screen, but you're not really. You are just relying on the hardware to render a completely transparent portion of the sprite for this particular bank in the bitmap data, because the bank which is displayed for the bitmap data for the status panel, the status panel only appears in this VIC bank. So the VIC bank is changing as it's going down the screen, and the other VIC bank displays the bitmap data for the second screen, but it's only one screen for the first bitmap in the first VIC bank. The VIC bank at 8000, right? It's only that data which draws the status panel, but it also allows you to then kind of like magically clip the sprites to within the narrow horizontal band for the rendered view, and to not obscure the status panel, which is quite a nice way of doing it. It means that the hardware does it for you for free, effectively, instead of trying to do all of the difficult stuff with moving sprites off the screen and to have a raster split there and everything like that to get sprites to move off. And it means that you're not trying to aggressively keep the sprites within the narrow range. I mean, you could, because you're dynamically updating the sprites, you could do all of that calculation to software clip your sprite data as well, but you don't need to, because the hardware will do it for you, because it's rendering an empty sprite frame. So yeah, this is a really cool game. For the time period when it was released, it's really impressive. The graphics rendering was really very impressive, and it still impresses me today, considering the constraints of the screen. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.